I'm Steve Moorman. I'm from Babcock and Wilcox. I've been in B&W for 40 years, and I tell people that I'm walking, talking proof that you can breathe coal dust and fly ash and NOx and SOx and mercury for 40 years and live to tell about it. So anyway, I came to Barberton about 7 years ago. I've worked in the field for a long time as a service engineer and in sales, and I came to work in our advanced technology group, which at that point was certainly developing both of these two technologies I'm going to talk about today, oxy-combustion and post-combustion capture. So it looked like a road paved in gold, clearly lit, looked like a lot of things were going to happen, and in a very short period the lights went out and the weeds grew over the road, and we're not quite sure today where carbon capture itself is going to end up. But certainly without a law of driving us to a clear direction for capturing carbon, it's been really hard to get this stuff off and on the drawing board. This is just a quick picture of it's actually the FutureGen CO2 capture project that we're involved with in Maridoche, Illinois. It's one of the DOE's original 10 large demonstration projects. I'm going to talk about that just a little more, but if you know anything about a power plant, that looks like a power plant. It looks like every other power plant we've ever built for pulverized coal. So one of the things we like about oxy-combustion, it's not so different that it scares people. Not that the cost doesn't scare you, but at least the technology itself looks pretty simple. I tell people I always kind of start out to let you think about the whole process of carbon capture, but it's a huge difference between capturing CO2 and capturing mercury and SOx and NOx. And if you just look at a 600 megawatt plant, produces maybe 1,000 pounds of mercury, 8,000 tons of NOx, 27,000 tons of SO2, 150,000 tons of ash, and 4.5 million tons of carbon dioxide. So it's just a completely different scale of effort that it's going to take if we're going to do this on a large scale, not only in the U.S. but around the world. Just to talk about oxy-combustion itself, at least for PC oxy, it's a process that basically you extract the nitrogen out of the oxidant that you use to combust the coal. So in our case, nitrogen is about 80% of what's in the air. You replace that nitrogen with CO2 that's recycled from the back of the flues in the boiler as the boiler operates, and I've got a little graphic that shows that. And basically, you combine that CO2 with pure oxygen or nearly pure oxygen from an air separation unit, and basically you make synthetic air. And why the boiler looks like it looks, like every other boiler, is you make this synthetic air look a lot like ambient air with the percent of oxygen in it and the amount of CO2 that's in it. So the boiler can't tell the difference between that it's firing this low nitrogen oxidant. Once you produce the CO2 at the end of the boiler, you clean it with a compression and purification unit. It's fairly clean, pure CO2. You still have to extract the sulfur that you generate, SO2 and NOx, and mercury that you produce in the combustion process, but the stream of CO2 is highly concentrated. So this little graphic kind of shows that. If you look on the left is an ambient air-fired boiler, basically round numbers, 20% oxygen, 80% nitrogen. You fire the coal, combine that with coal, and you get some amount of CO2, but the nitrogen kind of passes through gets a free ride. What you end up at the back of the boiler is you see there's very little conversion of the of the nitrogen. I mean, it passes through, the oxygen combines with the coal to form carbon dioxide, and you also get moisture from actually that's part of the coal when you combust it. Either comes in with the coal or some hydrogen that might be part of the coal content itself. And then you still have a fairly huge volume of gas you have to treat at the back end of the boiler. In the oxy-combustion process, you recycle a large amount of flue gas from the back of the boiler, and what you end up with is a fairly large volume of CO2 coming in, a larger volume of CO2 at the exit of the boiler, and then you recycle a large piece of it, and the little short orange bar is actually the piece that goes to storage, to final cleaning and compression. And if you think about it, that little tiny bar, if you could combust coal with pure oxygen, that's about how much flue gas you could generate. Unfortunately, we can't make the boiler work with that little bit of flue gas. We actually need the full volume of flue gas to make the heat transfer services work. So that's the reason we have to recycle the CO2. Just kind of talk about how long it's taken to get where we are. I mean, we started development of oxy-combustion back in 2000. It's now almost 2015. We've been working on the Future Gen project again, which would be the largest in the world oxy-combustion capture, transport, and storage project. That's been going on since about 2010. Hopefully, we're going to get it to the finish line. It's certainly not been easy, even with $1 billion of government stimulus, so to speak, to get the plant or the project to go. But a lot of the issue is how commercial is this technology, and we're having to go borrow a significant amount of money from the commercial market, and the commercial guys want commercial guarantees, which to this point we as a supplier are not willing to make, at least at this point. So until you get one of these things running and get some knowledge about how it works, I mean, we're reluctant to make a full commercial guarantee on this project. This talks a little bit about net plant efficiency, and Angelo's talked about it, but if you look at efficiencies on the far left-hand side, that's air firing without capture. You can see some pretty high plant efficiency values. In fact, that case 2 is, that's an advanced ultra-supercritical plant, which is only a projection because nobody's built one yet, and we're trying very hard to get that technology off the ground, but it requires certainly some development of special metals that are available, but not in the quantities that you need, and there's still a lot to be learned about that. Actually, the average, probably, I made the number that Angelos had. At 10,000 BTUs a kilowatt, that's a plant efficiency of about 34%. The average plant in the United States today is about 32%. Ultra supercritical plants, which are the plants that have been built most recently here, probably over the last 5 years, they're pushing it to about 38, maybe 39%, depending a little bit on the fuel you burn, just the losses with water and moisture and other things. But then you move over to the center one, which is you add carbon capture to the process and you see what happens to the efficiencies. It's a significant reduction in efficiency, net efficiency, basically because of all the auxiliary power required primarily to operate the air separation unit, which is a huge power draw, and everybody's got the same problem no matter what your technology is. If you're going to compress CO2 and store it, the compression energy is pretty significant as well. So you see a fairly large drop in efficiency. And this is just a levelized cost of electricity. That just reverses, right? The higher your efficiency is, the lower your cost of electricity is. The lower your efficiency is, the higher your cost of electricity. So what you see is these air-fired plants that are maybe producing electricity at 7 cents. Now you're at plants that are producing at 10 or even higher. And for us at Future Gen, our projection is that it's almost 16 cents a kilowatt to produce from our first CO2 capture, PC CO2 capture.
Which rate are you looking at?
This would be 90%. And for oxy-combustion, I don't know if it's a pro or a con, but it's an all or nothing deal. You can't do partial capture if you do oxy-combustion. You're going to do 90+%. I mean, and I think actually the Future Gen project is predicting it could capture up to 98%. I think going in, initially we talked 90 to 92%, but I mean, it's a very high capture rate. Again, looking at CO2 capture, the piece in the middle is the power plant, and you've seen other pictures, but you know, boiler, fans, fabric filters, scrubbers, coal bunkers, all those things. Well, and the reason I show you this is the air separation unit at the top that produces oxygen, and the compression and purification unit at the bottom, which will clean and compress it. If you'll take those two pieces, they take up as much real estate as the power plant. So now again, we were talking, I think, about retrofits and whatever. It's a significant problem if you think about existing plants and the potential to retrofit them with that much equipment that has to be added. So new plants, maybe not such a big problem, but still a lot of real estate it takes to make oxygen and to compress the CO2. There's some things that we like about oxycombustion, particularly PC oxycombustion, and that's, like I said at the start, it looks like a plant that we built before. It's made out of the same materials, it's got the same equipment in it, it's going to operate very similar, so plant operators and plant owners that look at this are not scared to death by something that's just, not that this isn't new and isn't complicated, but it certainly looks a lot like what they've done before. We've done pilot testing. We B&W, I think the largest oxy plant running right now is maybe, it's 10 megawatts. I think it was in Germany. I'm not sure it's still running, but we tested at about 3 megawatts electric. And what we found is it really does look like it's going to operate like a normal plant. The heating surface and the heat transfer rates are very similar. We're going to crush the coal the same way. The burners are slightly modified, but again, nothing drastic. The AQCS or gas cleanup system in the back looks like it's going to operate just like every other one. So water dry scrubber, bag houses, mercury control, all those things are going to be the same. And the basic process controls are going to be the same. Other than the transfer, and for this particular plant design, we'd start up on air, and then we would transfer to the oxy firing conditions. So, you know, it'll be a little tricky in the transition, but once it's done, again, it should operate just like a normal plant. We can use any kind of coal as long as the boiler is designed for it. It's not a problem. If you're going to retrofit or repower, which I think is going to be hard, personally. I mean, we are repowering the plant in Illinois, but basically we're ripping out the old oil boiler that was there and replacing it with a coal boiler. I think it's going to be hard just to retrofit an existing boiler, but it might work. It's less complicated from the standpoint you don't have to dip into the steam cycle for anything, and I'll talk about that when we get into the post-combustion capture piece. But that adds a real level of complexity when you're trying to regenerate solvents in the post-combustion capture, where that energy has to come from. But that is not the problem here. Basically, the ASU and the CPU are just a big electric load, and that power can come from anywhere. We really don't introduce any new chemicals or waste streams, so the FGD output and the bottom ash and fly ash is all going to be the same, so there's nothing new there that a plant operator would have to learn to manage. Again, all those streams are going to be the same. There's no change to the plant water balance, except, in fact, for some fuels, we need to add a polishing scrubber to the end before we send the gas to the compression and purification unit, and actually we'll pull water out of the flue gas. So in some cases, we may actually have a positive water balance. We may actually produce water from this process. Like every new thing, there's also some challenges. It's very expensive. The air separation unit and the compression and purification unit don't quite double the price of the plant, but they come pretty close. And I say that's definitely a challenge, but it's a challenge for every CO2 capture, whether you're doing post-combustion or IGCC. There's extra equipment that has to be added. There's additional auxiliary loads that are taken that everybody's got the same problem. And then same comment, auxiliary power. Everybody's going to use a lot of aux power to either make oxygen or compress CO2 or regenerate solvents. Oxy is not a partial capture, so either going to capture 90% or whatever, or you're not going to do this. The thing that we haven't proved to ourselves, and that's, can you make the boiler and the air quality control system and the compression unit and the pipeline and the storage facility all operate at the same time on the same day? And that's one of the big things we hope to learn. We hope to learn at FutureGen. So, starting up, shutting down, can you swing load? Certainly load swings with CO2 capture certainly doesn't make it easier. And again, just a nice picture of the plant. This is a drum boiler, but looks like every other drum boiler we ever built for this capacity. It's about 150 megawatts. Air heaters, fans. This is a circulating dry scrubber baghouse combination. So there's your FGD control and ID fans back here. All that recirculation of CO2 is kind of buried in here somewhere, but this little fairly small pipe back here would be the exhaust to the compression and purification unit. So that's where the final CO2 would be extracted. Just talking about what we're going to try and accomplish at FutureGen, we certainly have done a lot of engineering to this point. We hopefully are fairly confident in the cost. We're at like $1.7 billion right now for a 150 megawatt plant, which is and a pretty astounding number. The last one we built was about $400 million, so you can see what the cost capture does. A lot of things we want to learn, primarily around the boiler, but how reliable is it going to be? Can we maintain it? This plant itself was not designed for high efficiency. It's not a supercritical plant. It's a drum boiler, but at least in our mind, at this point in the technology development, going to higher efficiency was only going to add additional cost, which we're already pressing the budget. So it really wasn't going to teach us anything about the technology, the Oxy technology itself. We think if we can make this work, we can easily transfer this to a higher pressure design or a higher efficiency boiler design. We just want to prove the basic concepts of how this thing is going to work, and once we do that, we can move to higher efficiency and larger capacities. We just got to learn some things about the process. Can we operate it safely? Can we start it up and shut it down? Those kind of things that you need to learn with any new technology. And then the big piece is, again, integrated operation of the boiler and start with the ASU. Can we get oxygen from the ASU, bring it to the boiler, clean the gas, send the gas to the CPU, transport it, and store it at the storage facility. So lots of primarily operating things we want to learn from FutureGen. This is a real quick, this is like the next step in oxycombustion. This is chemical looping, and what happens here is in lieu of operating with an air separation unit, you basically take a particle that's we call an oxygen carrier. You can mix it with coal. I tell people it's more like a hot pack and a cold pack. You can break chemicals and put them together, and depending on what they are, you get cold pack or you get a hot pack. The same thing is happening here. We're processing coal, but we're really not combusting the coal. There's no flame involved. It's strictly a chemical reaction. The problem of it is that you react that coal particle in a furnace in about 3 seconds, and it takes about 30 minutes to react it in the fuel reactor. So you can kind of guess how big that furnace got if it takes that long to process the coal. But you then take that particle, you can flow it over to a regenerator, you basically blow air through it, and you reoxidize that particle, and it generates a whole lot of heat, plus it puts the oxygen back in the particle, and you recycle the particle back to the fuel reactor. So it's the looping part of that where it comes from. But again, because there's no nitrogen and it's purely this iron pellet as the oxygen carrier, no nitrogen involved, the coal reaction process does itself produce a pure stream of CO2. So hopefully it'll be the next step in oxycombustion. It looks like from the paper studies it's going to be less expensive, but it's out in the future. It'll be way past my retirement date, I guarantee. So again, just chemical looping eliminates the air separation unit. It's a chemical process. It's fuel flexible. And it can also be used with other syngas and other things to produce liquid fuels. So there's some other benefits of the chemical looping process. It does produce pure CO2. And again, can be used in other processes to make hydrogen or liquid fuels. And we've been working with the Ohio State University for this for about the last 10 years, and we're doing a project down at the National Coal Carbon Capture Center at Southern Company on a syngas project. That's kind of in process right now, and the thing we're talking about at whole is coal direct. So we're going to try and find a way to do put coal directly into this process. Talk a little bit about post-combustion capture. I'm not sure how familiar you are with it, but it's very similar, in my personal opinion, and I'm not a chemical engineer, I'm a mechanical engineer, but very similar to a wet scrubber process. Basically, you're passing gas through a liquid. The liquid extracts the CO2. The other gases are vented out, primarily nitrogen. You then can take that solvent that's got the CO2, the rich solvent as they refer to it, in it. You take it into a desorber or a regenerator. I refer to it as boiling off the CO2. It's not really fair to call it like that because you can't boil it. It'll damage or it'll destroy the solvent itself if you get it at too high a temperature. But you raise the temperature of that solvent, it allows the CO2 to release, and you can then send it to the compression unit and compress and send it to storage. The options right now for post-combustion capture are not only this process that you just saw, but other types of sorbents and other types of systems. This regenerable solvent system is really one of the first generation CO2 capture ones that's out there. Integrated gasification combined cycles, one, oxy-combustion is the second, and post-combustion capture is the third, which I refer to as first generation systems. The chemical solvents and the physical solvents have been used in that process for a long, long time, primarily in the chemical business, certainly not in the utility electric generation business. People are trying to develop solid sorbents. There's certainly some advantages where you don't have all this water involved that you got to heat up and cool down all the time. The problem of it is you got millions of tons of solids that you got to move around. And for boiler people, moving solids around is not a good thing. It's energy. B, you got to move them around without doing damage to them, which that's an issue. You know, how many of these particles are you going to have to replace? Right now, they're fairly expensive, so the less damage you can do to them, the better off. There's membranes out there that are basically fabric filters that are able to separate gases, so you can separate oxygen, you can separate CO2. There's good things going on, but it's still at fairly small scale. And then some of these other biocatalysts, lots of crazy things there. If you're a chemist, I'm sure they're happy as clams with some of the stuff they can do, but it's been very hard so far to seem to be able to scale those technologies up. Where I refer to them as jelly jar size things that they just can't seem to get past that scale. And when you're talking about a power plant that's going to need millions of tons of solvents and sorbents and membranes, they got a long way to go. And then cryogenics have been used, but cooling down gas is very expensive when you're talking about the volume of gas we have in a power plant. This solvent selection process, and I've kind of alluded to this a little bit, I mean, you use a lot of it, and you want to find the least expensive way the least expensive product that you can, and a lot of things go into that. How fast does the solvent absorb CO2? How much CO2 per pound of solvent can you absorb? What are the requirements heat-wise to regenerate the solvent? How fast does it degrade? Are you going to have to replace it a little bit, a lot, often, never? A big thing in both the cost and environmental impact, depending on what the solvent itself is. If you got to throw it away, then you got to find a place to put it. Volatility, solubility, all the things you can see that go into your decision on what kind of solvents you're going to use. And certainly, there's a lot of people besides B&W trying to figure that out. Our chemists seem, I don't want to say what the word is, they're not real positive about how much better you can make the solvents that are out there today. So, I mean, they're trying, certainly the right combination of promoters and other things make them better, but they think we're fast approaching the limit of how good they can be. Again, just a picture of it, but you put flue gas in, you rain the lean solvent down through it. Typically, these absorbers have some kind of packing inside to help the contact between the gas and the solvent. You take the solvent out the bottom, the rich solvent that's got the CO2 in it. You pump it over. This process itself is exothermic. It generates heat as the solvent is extracting CO2 out of the flue gas. So you do some heat exchanging before you put the solvent into the desorber. And again, basically you rain the liquid down, you put heat into the bottom of the desorber, and it drives off the CO2 gas. Again, you catch all the solvent in the bottom, pump it back over, and the cycle just continues. While these amine solvents and physical solvents have been around for a long, long time, typically they've been in chemical processes that operate at fairly high pressures, very high pressures relative to these, 300 to 500 psi. The problem you got in a power plant, it's almost atmospheric pressure, right? So you're talking about maybe up to 15 inches of water, but less than half a psi. So I mean that's a big differentiator. I mean a very small tower at 500 psi turns into a huge tower at atmospheric pressure. So again, low pressures, big vessels. 11 to 1,200 BTUs per pound of solvent or per pound of CO2 to extract from the solvent. So a fairly big energy consumer. You got to find that energy somewhere. It's got to come out of the plant. Typically, we've talked about dipping into the turbine cycle and using extraction steam out of the low pressure end of the turbine, which reduces the output of the steam turbine, also doesn't help the efficiency of the turbine. It's now not in balance anymore based on the original design. A new plant could be a little better, but trying to do this in an existing plant is definitely going to make an impact on the turbine. It's a large equipment footprint, and I'll show you another couple pictures. Certainly going to impact the flexibility of the plant to load cycle. Managing solvent inventories and waste is going to be a lot of it. It's a whole nother level of difficulty for operators. And if you're going to use energy to regenerate the solvent and energy to compress the solvent, now you got to find something, you got to replace that energy somehow. It's got to come from somewhere else. So if you got a 500 megawatt plant, you're going to take 25% of it. Now you got 200 megawatts you got to go find back that's not available to your customers anymore. Just a real quick picture. This is the polishing scrubber. You need to get the SO2 levels down very low before you put it into the absorber. This is the absorber tower. This is the regenerating tower. If you can see down here, this is a little guy. It's a little tough to see, but just kind of give you some idea what the scale of this is. This is 200 megawatts. This is a wet scrubber. There's 3 of them. I think they were at Hatfield Ferry. Each one of those towers is 600 megawatts. So if you take these 3 towers, that's 1,800 megawatts, and you figure out that footprint of that 200 megawatt absorber, desorber was almost as big as 1,800 megawatts footprint of 3 wet scrubbers. You got some idea of the amount of real estate it's going to take to make this, to put this, the post-combustion capture systems in. And just from a status, there's certainly been some small projects out there. The biggie, and it's just been announced, I don't know if you've seen it in the news, but NRG at the Parish plant down in Houston is about to cut loose their 240 megawatt amine system. Would definitely be the biggest plant of its sort anywhere in the world for a amine-based capture system on a power plant. They're going to they actually bought into an oil field to make this process or project happen because they're going to use the CO2 for enhanced oil recovery. Certainly people like B&W and a lot of other people we're still working on amine-based systems along with other kinds of sorbents and solids, membranes. I mean, there's a lot of work going on. Fortunately or unfortunately, most of it's going to take a while. The big problem that I see, and this is Moorman talking and not Babcock and Wilcox, is that there's such low growth in coal-fired business, regardless of regulations or anything else. It's just hard to get to the nth design, which is the low-cost, high-efficiency piece. And you look at the costs of what are here today, and they absolutely scare people to death, particularly a utility guy that has to go buy one. And if you've kept track of what's gone on at Edwardsport and at Kemper County, which Edwardsport was an IGCC project without capture, and you look at Edwardsport, which is an IGCC project with capture, both of them came in at almost double their estimated cost, which is, I mean, you build a conventional coal plant today, lock, stock, and barrel, $3,000 a kilowatt, and you know, Kemper County is going to be 7,500 or 8,000. It's a huge number that's going to scare people, and I'm not quite sure how big a price you can put on carbon to convince somebody to build a power plant, but it's a pretty tough sell right now. And I talk a little bit about demonstrations, and I know there's a little disagreement between EPA and the industry about where we stand on commercialization, but you know, none of the stuff that we've done we certainly feel is commercial, PC Oxy or post-combustion capture, but these demonstration projects that are out there now that DOE are doing are very important to make not only guys that build plants, but the guys that have to operate plants, make them feel comfortable that this is really something that they can do and A, not break the bank, and B, operate for a long, long time and get their money back. So, you know, these demonstrations do really establish confidence. You know, they give you assurances that the plants are going to work like they're designed. They're going to prove you can make the emissions that you say you are. It's got to be safe. That's a big thing everywhere. If you've got a demonstration plant and you got some iron in the ground, now you can take time to optimize and make the next process better. You got to prove that you can make it work financially. No doubt about it. Nobody's going to buy one that they can't make money on. Once you got steel in the ground, you can look at things and find out where the weak spots are and where the improvements can be, and certainly develop specifications and methods for the next generation of systems. So I think with that, I'm done. Any questions? Yes?
Where's the next gen plant going to be located? I mean,
Future Gen? It's in Illinois. It's about 100 miles north of St. Louis, right on the Illinois River. It's the old Ameren-Meredosia plant, which it's a plant that's been there probably since the 40s. The newest part of it was built in '74, and we're going to blow up the old oil-fired boiler and replace it with the oxy-combustion boiler.
Steve, if you were in an oxy-combustion like that, if you were to do a true retrofit to an existing facility, so you're saying the heat flux for the boiler tubes and everything for retrofit is still okay?
You know, it's not going to be perfect, but we could make it work. I mean, or you could do modifications to it without literally having to knock it all down and start over. But the problem you got with older plants, the big thing you don't want is you don't want air leaking into the system, and that's the problem you got with an older plant. It's going to be, are you really going to be able to stop all the air leaks? I mean, Angelo's talked about excess air as being a loss. It's a real loss in an oxy-combustion plant. I mean, now you got to process that air through the compression purification units, so it's definitely an added expense. And the other issue is typical with older plants is the amount of real estate you need for the air separation unit and the compression purification unit. This air separation unit won't make liquid oxygen, but you could make liquid oxygen, and you could build the ASU bigger than it needed to be. You could make liquid oxygen. You could turn the ASU off, sell the power onto the grid at peak periods, and use the liquid oxygen. It's just back to a economics balance of what you're going to try and do. And in this plant, I mean, certainly, like I said, for this particular plant, I mean, we've been trying to whittle the cost down, and we're still busting the budget, but hopefully we're getting close. All right, almost.